Hi everyone, welcome to Power session number 20. In this session, we discuss SMPS. SMPS means switch mode power supplies. These switch mode power supplies generally used for IC circuits. In those IC circuits, load is always resistive load. Hence, in SMPS, filter is must to eliminate ripple voltage and ripple current. Okay, so in SMPS, there will be three different type of circuits. One is buck converter. It is nothing but step down converter. In this case, output voltage is less than or equal to input voltage, nothing but stepping down the output voltage. Okay, so second one is boost converter, nothing but step up converter. In this case, output voltage is more than or equal to source voltage, nothing but stepping up the source. So here this more or less we discussed in case of choppers both the circuits, but now we need to discuss with a little bit different. Then third one is combination of these two, that means buck boost converter, step down and step up converter. So in this case, output voltage V0 will be less than VDC, nothing but it is acting as a step down converter if duty ratio is 0.5, it's less than 0.5, and it will act as a boost converter if duty ratio is more than 0.5, nothing but output voltage will be more than input voltage. So it will act as a buck converter for duty ratio less than 0.5. It will act as a boost converter if duty ratio is more than 0.5. And if you are maintaining the duty ratio at 0.5, then output voltage exactly same as source voltage. So that's it. So as I told you, in these SMPS, main switch will be MOSFET because of the high speed operation mainly, but some cases we can go for IGBT, and for gate exam point of view you may see in some circuits BJT also. Okay, but mainly we will go for the MOSFET. Why MOSFET is required means that is because of the high speed operation, high switching circuit. Okay, high frequency. Why high frequency is required, that we will discuss in the coming sections and we will see that. But here in our discussion we will not use any of these main switches. Instead of that we go for simply mechanical switch. Okay, that means what's the representation of the mechanical switch? In place of this, any of these switch can be used. Okay, that's the meaning of that. In this session, we mainly concentrate on the buck converter operation and respective waveforms. So in this case, here you can see that buck converter is more or less same as the step down chopper what we discussed, but the additional thing is nothing but this portion. This is nothing but filter. We use LC filter. This is generally called low pass filter. Okay. That low pass filter is required to filter out the ripple content which is actually there in output of the current and voltage. That means this resistance will expect constant value of the load current. That means this is DC current. Okay. Why I'm actually telling DC current? This will not have any ripple. That's what we need to maintain. And this voltage is also constant DC voltage. To maintain this, we need to design what LC circuit is required. Okay, but if without this, if you're operating this one in the switching mode, then obviously the load voltage will be kind of like a pulse drive. In that case, you will have a lot of ripple content, what we discussed in case of step down converter or step down chopper. So to eliminate that, nothing but to maintain the constant current and constant voltage, we need to have a filter. That is what our aim. So here we will operate this switch S only. That means turning on, turning off. If you turn on this one, then source will be connected to the load through the filter. In that case, the source voltage will appear across the diode, but that will appear like this, positive, negative. That's why this will be open circuited, nothing but reverse biased. So we'll see now what will be the equivalent circuit during T on. T on is nothing but when the main switch, either IGBT or MOSFET is, or BJT is in conduction. In that case, this will be, that means you can say this switch and this switch are mutually exclusive. That means when the switch is in conduction, this will be open circuited. When the switch is in off state, this will be in conduction to maintain the load voltage and current of constant. So as I told you that, you can see here when the switch is on, that will act as a short circuit, and this is open circuit. And now you will see that this source is supplying the energy to the load through the filter. So now I represented few currents here. This is the source current IDC, this is the switch current IS. These two are always same in this case, because when the switch is in conduction, then only source will supply the energy to the load. That means these two currents are same. Then this IL is very important. This is the inductor current that we need to discuss more about that. That inductor current is actually splitting into two portions. Nothing but one portion is nothing but load current I naught. This is average value. That means what inductor current will have a kind of like a combination of two currents. One is like a kind of AC and other one is DC. Whichever the DC portion is there, that is flowing through the load resistor, and remaining AC portion will be flowing through the capacitor, because capacitor will not allow the DC voltage or DC current. That's why DC current or DC portion will be flowing through the load, and AC portion, that is generally called as a ripple, that ripple will be flowing through the capacitor. That means simple thing, it's like a kind of like adding some AC portion plus DC portion is nothing but inductor current. So remember that. In this duration, inductor is getting charged along with the charged by the source. That means inductor is charging. That's why this is positive polarity and this is negative polarity for the inductor voltage, and current is flowing like this. Okay, so that's the on duration. In this on duration, we need to remember important thing is what is the inductor voltage VL equal to. You can see that load voltage is nothing but VC. The same thing will be appear across the capacitor. Okay, because both are in parallel. So now in this loop, you can see that source voltage is nothing but voltage drop across the inductor plus capacitor voltage. Inductor voltage plus capacitor voltage is equal to VDC. From that equation, VL equal to VDC minus V0. And inductor is getting charged. Nothing but in this loop, this is acting as a load, this is acting as a load. Then in that case, source voltage is nothing but sum of this voltage drop plus this. Okay, so from that equation we are getting VDC minus V0. Then in that case, to get the variable voltage at the load, we will turn off this switch, conducting switch. Then in that case, this inductor current actually forcing the diode to be turned on. So in the duration, you can see when switch is turned off, then this will be open circuited, and now this inductor current is actually forcing the diode to be turned on. So that means inductor current is actually flowing through the diode, that is the diode current. Both are same, diode current and inductor current. Now you can see during this period when switch is not in conduction, this inductor will actually supply the energy to the load to maintain the load current constant and voltage constant. So in this case, this inductor will act as a source. That's why you can see that current will be same direction, because inductor current will be like a kind of, you can say, charging current direction, and discharging current direction will not be changed because it is acting as a current source, but voltage polarity will be changed based on the charging and discharging. So now it is discharging, that's why voltage polarity is reversed, but current will be same. So now whichever the DC portion will be there in the inductor current will be flowing through the load, that is nothing but is always drawing the load current constant, and remaining AC portion, which is called ripple, will be flowing through the capacitor. So in this case, you can see that this is the source voltage and this is the load voltage. Load voltage is V0. So in this loop you can see that this VL equal to V naught. So in this way, during this period, inductor voltage is nothing but V naught. But remember, this direction we are assuming positive, but this is negative side. So now we need to draw the waveforms related to these things. Okay, we'll discuss one by one. So we are going to discuss about the 4 waveforms. Okay, so what are those 4 waveforms? I'm actually taking like a T on duration, T off duration, T on, T off, T on, T off, like that, because based on these waveform, circuit diagrams, we are going to draw the waveforms for voltage across the inductor. That means VL. We discussed already what is the voltage during the on duration and during off duration, because the circuit is related to half duration. Okay, and then inductor voltage, then inductor current, capacitor current, and finally capacitor voltage. Okay, so these are the things we are going to discuss: inductor voltage, inductor current, capacitor voltage. But remember, capacitor voltage is nothing but the output voltage. Capacitor voltage and output voltage both are same. Indirectly we are talking about VC, means it is nothing but V naught only. Okay, you can actually take this one as a V naught. Both are same. So as we discussed here already, inductor voltage is VDC minus V naught during on duration. That means here VDC minus V naught, that is a constant. This is a constant voltage we are maintaining, and this is also constant voltage because DC. So in this duration, inductor voltage, you will see that input voltage minus output voltage, that's a constant voltage. When the switch is off, you can see that VL is equal to V naught. So that means, but this is the opposite to the previous one. That's why we are drawing on the negative side. So likewise, if you turn on the switch, turn off the switch, you will get the inductor voltage like this. Look at here, during T on, inductor voltage is constant, means in this case inductor is getting charged with the constant DC voltage. If the constant voltage is there, then obviously current will be linearly increasing. That's nothing but ramp, but it is actually charging, that's why it is increasing like this. And then during off, that means when switch is off, you can see that inductor is acting as a source. In the duration, it is discharging with a constant voltage again. So discharging with constant voltage means again the current will be ramp, but it is a decreasing current. Likewise, we will have the current waveform like this. Now we will apply the limits on this. That means this is a IL min and this is IL max current. Okay, this is always will be flowing like this only. It reaches the maximum current, then coming to minimum current, maximum current, minimum current, like that. Okay, so if you take the average value of this current, inductor current, it will be exactly in the middle of this one. That means if you take that, average value of the inductor current is exactly in the middle. This average current is flowing through the load all the time, and whichever the ripple current is there, that will be flowing through the capacitor. That is why if you take out this average value from this inductor current, then the remaining ripple will be flowing through the capacitor. Okay, remember, if you take out this average values, similar ripple current, exactly similar, this is actually oscillating about average value of the inductor current. If you take out this average value, the same current will be that means the ripple current will be oscillating about the zero. That current will be flowing through the capacitor. Okay, so if you add this ripple current plus average value, then you will get the inductor current like this. Okay, so that means always inductor current is splitting into two portions. The average value is always flowing through the resistance, and the remaining current is flowing through the ripple current is flowing through the capacitor. That's the meaning of this. Now look at that. Capacitor is actually current is increasing linearly. During this period, capacitor voltage will be parabolic. Okay, so but parabolic, how the exactly parabolic? Whenever the capacitor current is actually minimum, then voltage will be maximum. That's why you can see like this. Whenever this is actually maximum, then it will be minimum again. Okay, likewise it is discharging, then it is actually like again constant current, that's why linear current or ramp current, that's why voltage will be again parabolic. Likewise capacitor voltage will be oscillating, but this capacitor voltage will be oscillated about the average value. Its average value is nothing but output voltage V average. So this is capacitor ripple. So these are the waveforms will be for buck converter. So these are the waveforms we already discussed. Now we can see that the difference between the max inductor current and minimum inductor current will be represented by delta IL. Okay, this is called peak to peak ripple current in the inductor current. This I average is exactly in the middle of max and min, that's why it is exactly in the middle of this one. So now we can see that this difference is nothing but delta IL by 2. Okay, that's what. So now this exact ripple, that means this peak to peak is nothing but delta IL only. That's why this height is again same as what we discussed here. So that's nothing but delta IL by 2. And as we discussed in the first class, the average value of the capacitor current is always 0 for the periodical voltage. That means to apply the same condition here, so this area under this curve plus area under this curve must be equal to 0, then only this current will be 0. So average current, that is why this height is actually same as this one, so that's why base must be same. So from year to year it is one time period, that's why from this to this one is half of the time period. Okay, so these are the things, and we need to look at this maximum value that is happening exactly at this location, and minimum value is happening exactly this location. So that max and minus minimum is again represented delta VC. So this is called as peak to peak ripple in the capacitor voltage, nothing but output voltage. So output voltage ripple and here inductor current ripple. So our intention is like to calculate this one, then remaining other things. So now look at here, to calculate the delta IL, that's nothing but peak to peak ripple current in the inductor current. You can see that that's happening, that's a change in inductor current happening from minimum to max or max to minimum. That is happening in the T on or T off. You can use any one of that. So you can use the T on. So as we already discussed, like in many sections, inductor voltage VL equal to L into di by dt. That means dL by dt. That can be taken as a L into delta IL divided by delta T, because if the current is following linear curve, then we can actually take the differentiation as a difference equations. The same thing you can take. So during this period, the voltage across the inductor will be this one. That is why we can take it as a VDC minus V0 equal to L into change in current is delta IL divided by how much time it is taking? T on. So that you can take it as a T on. So from this, peak to peak ripple current delta IL equal to, you can say that is equal to, so from this VDC minus V0 into Tn can be taken as a D times T. Okay, so because duty ratio is nothing but Tn by T, so from that Tn equal to dt, so whole divided by L. Okay, So this is what you can take. Otherwise you can actually take that T as a 1 by F. That's why you can see this can be taken as a VDC minus V naught into D by F L. That also can be taken. Okay, remember this equation. This is what important for us. Okay, if you look at here, delta IL is actually more, means more ripple will be there. That is nothing but we require more and more inductor value or filter value. Okay, so to maintain this 0, that means if it is 0 means almost like load current is always constant. To have the minimum ripple, we require either use inductance value, or you can see that T is nothing but 1 by F. Switching frequency must be very high. That is why we will always operate the SPMS with very high frequency to maintain the load current constant. That means to have the less ripple in the current. Okay, less ripple means it's almost constant. So that's what. So from this waveform, you can see that IL max is IL average value plus delta IL by 2. That means IL max is nothing but average value of the inductor current plus this portion. So that's what that is. Likewise, IL min is nothing but IL minus delta IL by 2. So look at here. So this minimum value is nothing but average value minus this portion. So that's why this one. We calculated delta IL by using this equation. To calculate the max and min values, we need to know that IL average value of the inductor current. Remember, these are the maximum values of current flowing through the inductor. That also you can take that because switch is on during this period, same maximum current is flowing through the switch also, and same maximum current coming from the source also. So these are the things we need to remember to answer some of the questions in the which are given in the GATE exam. Okay. So good, to calculate the max and minimum value we require these things, but we need to know that IL thing. So I already told you that in case of buck converter, average value of the inductor current is always nothing but I average, because the same average current is splitting into, that means flowing through the load. That's what I told you, that inductor current is actually splitting into two portions. One is average current that is flowing through the load, and ripple current that is flowing through the capacitor. So that's why IL average is nothing but load average current. But how to calculate the load current average value? Average value of the load current is nothing but V0 divided by R. But how to calculate the V0? V0 is nothing but just like a buck converter is nothing but step down converter. We can use the same equation what we discussed in the DC choppers. That means D times VDC. So we can calculate V0. From that we can calculate I0, then we can calculate IL average. So that's the meaning of that. Okay, so that's all. So another thing is like this is what we need to remember again in this. Okay, another thing is here we need to look at like this one. What is that? Power balance equation. Power balance equation is nothing but DC power which is supplied by the source is exactly utilized by the load. That means V0 into I0. In that case, you can take this V0 this I0 this side and V0 that side, VDC that side. Then IDC by I0 equal to V0 by VDC. So you can see that V0 by VDC is nothing but D, that is equal to D. So if you remember this equation, you can calculate, or you can have the relationship between source current and load current. Source current ID is equal to D times I0. So now we establish almost a relation among all the currents. We know the relation between inductor and load current. We know the relation between source current and load current. And remember, source average current is nothing but the switch average current also, because whenever the main switch S is in conduction, then only source is supplying the current. Okay, this is another thing. And remember, in this case, whatever the ripple is there which is flowing through the inductor, same ripple current is there in the capacitor also. That's why capacitor ripple current is also same as inductor ripple current. That means this can also be taken as delta IC. This is actually peak to peak ripple in the capacitor current, same as peak to peak ripple in the inductor current, because both the ripple currents are same. So that is what we need to remember. Okay, so another thing is here we need to calculate a peak to peak ripple in the capacitor. So that peak to peak ripple in the capacitor is happening between this and this instant, that is nothing but exactly this one and this one. So the same thing can be represented, can be calculated. So as we know that voltage, like a current flowing through the capacitor IC is nothing but C into dVc by dt. So from this, dVc can be taken as 1 by C integral IC dt. So this can be taken as a delta Vc, that is equal to 1 by C. So this integration is from some instant to some other instant of the time. That is nothing but like integral a to b f of x dx always indicates the area. So this is happening the like delta Vc is happening between these two instants. During that time we can take the area under the capacitor current. Okay, so that's what capacitor current into dt integral. So that area is nothing but half base is nothing but t by 2, okay, into h, that means height, that is nothing but delta IL by 2. So from this you can say that peak to peak ripple in the capacitor current is, capacitor voltage is nothing but delta IL by 2 into 2 into 2, 8, f, 1 by t can be taken as f and c. Okay, this is the peak to peak ripple in the capacitor voltage. Okay, why are we discussing about the peak to peak ripple in the capacitor voltage, peak to peak ripple in the inductor? So inductor current and all means these values will be given to you. That means delta L and delta Vc is given to you. We need to design the filter to have those values in the respective waveforms. That means you can see that if this is given and this is given, means you can calculate what capacitance is required for the filter. Likewise, if delta L is given, means we can calculate the inductance value. So like that. So here delta Vc is calculated. There is another one we need to calculate here. You can see that this inductor current is continuous current. Assume what will be the condition for the critical conduction. Critical conduction is nothing but this inductor current is touching the zero but not staying in zero. It is again flowing through the max value and coming to zero, moving to the max value, like that. That means it is neither discontinuous current conduction nor continuous current conduction. That means it is actually nothing but boundary between them. To have the boundary, that is called critical conduction. So this is very important here in case of SPMS, critical conduction. Okay, a critical conduction of the inductor current is nothing but, condition is nothing but this IL min actually need to be 0. Then only this current coming from 0 to max, then max to 0, then max 0 to max, like that. So that means IL min equal to 0. We already discussed what is the IL min. IL min equal to average value of the inductor current minus this portion. That portion is nothing but minus delta IL by 2. As we already discussed, in case of buck converter, IL is nothing but I naught. So from this equation, if you are actually equating this one alone, then I naught equal to delta IL by 2. But delta IL by 2 we already discussed, it is nothing but VDC minus V naught into D by FL, but 2 comes from here to FL. So that's what here. So this is the minimum average current is required to maintain the critical conduction. But most of the times it is asked about the inductance value, or asked about the duty ratio, asked about the frequency, like that and all. So from this we need to convert this equation to the required one, but most of the times we require the inductance. In that case you can take the inductance this side, L equal to, okay, so from this, so L equal to VDC minus V0 into D by 2F. I0 is nothing but V0 divided by R. R comes to the numerator. So again from this one, L equal to, you can take that VDC as it is VDC, but V0 is nothing but D times VDC, and this is D times VDC. We remember like V0 for the buck converter is nothing but, what is that, V0 equal to D times VDC. So from that you can take that V0 equal to D times VDC. So here VDC minus D times VDC, here D times VDC. D gets cancelled, and from this you can take common the VDC also. If you take common VDC gets cancelled, it is 1 minus D. So 1 minus D into R divided by 2F. Okay, so this is the inductance value required to maintain the critical conduction. Sometimes questions will be given like, okay, so what will be the resistance required to maintain the critical conduction? In that case, keep all the things this side, and resistance you can take this side. Sometimes it will be asked that what will be the duty ratio, then you need to take the duty ratio this side, like that. So this is a critical inductance. What is the meaning of the critical inductance here? So if so inductance value, filter inductance value is less than critical inductance, then the conduction is discontinuous. Likewise, if the filter inductance is more than critical inductance, then it is continuous current conduction. If the filter inductance is actually exactly equal to the critical inductance, then it is nothing but critical conduction. But mainly this equation is required, how much the filter inductance required to maintain the continuous current conduction or discontinuous current conduction. Likewise, these are the things required. Okay, so remember, these are all the things important. Okay, so I'm stopping with this, and then in the coming sessions we will discuss about other converters and respective formulas. Thank you.